Okay, all right, let's start then. So what we saw, today we're going to continue with sort of, basic properties of complex numbers, and we may get to the real object of study of the course, which is functions of complex variables and taking complex values. But today we'll still most of the lecture will still be just about properties of complex numbers, right? So we saw that if we had complex number alpha plus I beta, we define the conjugate as alpha minus I beta, right? So we just swapped the imaginary part. And sort of intuitively, I argue that nothing really should change, right? Because when I take I could have taken minus I as well, right? Because it's also a solution of x squared plus 1 equals 0, right? So the whole theory should be just the same with I and minus I, and indeed, we saw that basically nothing changes, and right? What we saw last time, if you take, right? This is sort of just housekeeping, right? There's nothing surprising about this. Maybe a little more surprising, I won't prove it, you have to do it yourself, is this. You just work out the algebra, and you see that this is true. And then if this is true, it's kind of clear that, if I take the conjugate of A divided by B, that this is also the conjugate of A divided by the conjugate of B. Right? For this, you just have, this now is sort of an easy implication of that. You just write x equals AB, right? And you just write the equation A equals xb, and the fact that you can put conjugates everywhere, right? And the fact that it's still the same this way gives you that you can also divide, right? So this is housekeeping, right? So in particular, this will hold, right, for any rational function, right? The fact that if I have any rational function, if I have, say, R or P, let me call it P, a rational function, right? So by a rational function, I mean the quotient of two polynomials, right? Let's say I take P of A, which is P one polynomial divided by another. Right? It's clear that this also holds for any that you can, right? The conjugate will be, you can take conjugates outside and conjugates inside, as long as you also take the conjugates of the coefficients, right? And in particular, it's not hard to see that if I have, right? So let me see. Let's say that I have a polynomial. Right? If I have a polynomial, equation of a polynomial being 0, right? Say if A is the root of this polynomial, right? Of that polynomial, so let me call it P of C. Right, then it's obvious that a bar is a root of the polynomial where I just take conjugates in all the coefficients, right? Because if I replace here by A and this is equal to 0, I can just take a conjugate everywhere. I get that the whole conjugate equals to 0, but the conjugate of 0 is still 0. And then I just get conjugates in each one of the C's, and conjugates in the Z's in some power of Z, but because the conjugate of a power is just the power of the conjugate, I get just that, right? C0 Z conjugate n plus C1 Z conjugate n minus 1 and so on is equal to 0, right? So C. No, Zn, sorry. This one, C2, C2. And so it's the root of this equation. I mean, I sometimes will say it's a root of the polynomial, or root of the equation is, of course, are all the same things. Right? To see this is of course easy. You just take so if you take this equal to 0, and now you conjugate it, right? This is still the same, but this is still 0, so I can delete here. Now the conjugate becomes the conjugate of each thing in the sum. Right? But this means that, because now I can take the conjugate inside the products. Right? And so if A is the root of a polynomial, then A conjugate is the root of the polynomial where the coefficients got conjugated. Okay, still nothing that surprising about it, but it already implies something that I'm sure you knew, but you didn't know that this would be such a simple implication of this, which is if these numbers C0, C1, all the way to Cn are real. Right? What this is saying is that if a number A is the root of a polynomial, then the number A conjugate is also the root of the same polynomial, right? Then in this case, what this statement will imply, right, is that if A is the root of a polynomial, I'll say P of Z, then so there's A conjugate. Right, the fact that for polynomials with real coefficients, the roots come in conjugate pairs. Right? If the root is not real, if it's complex values, then you will come in a conjugate pair. You get one number and a conjugate. Okay, so now let's move on to more interesting things. Okay, so we're going pretty fast on this part because, all of this you probably have seen in some form, and it's mostly just housekeeping of the theory, making sure that everything that you would want to be true, that it is actually true. Oh, I see everyone froze. Is there a problem on my system, on my side? Can you check if your YouTube stream is working? Okay, do you have audio now? Do you have audio on YouTube? Perfect. Right, and the image is fine and so on? Sorry, yeah. It's kind of amazing that we had to wait until second week to have an issue of this type. Okay, all right. If there's any problem, please just write on chat. Yeah, someone will address it. All right, okay. So the thing I told you at the very end last time was that that this is maybe a little less, a little more surprising. But that's okay, right? Or is anyone just hearing on Zoom?
On Zoom, no one's hearing.
But I did that so that I can unmute myself on. But maybe okay. Yeah, okay. I can fix it though. Okay. Yeah, I changed. It was my quick fix to make YouTube work was to change the audio on Zoom. Yeah. Okay. I think it's working. Okay. And now you have audio on Zoom too, if you like. Okay. So that that this is always positive, or then negative, right? Will be, of course, if A is 0, be 0, right? So if we have A be alpha plus I beta, right? Then what is this? This is alpha plus I beta, alpha minus I beta, right? And we know that this is alpha squared plus beta squared, right? And we decided to call A conjugate the norm squared of A. Right? It satisfies the nice property that it's always a negative, as you would like a modulus or a norm to be. But in fact, I mean, if you think of A as just an element of R2, this is exactly the Euclidean norm that you would define, right? So everything is completely self-consistent, right? And of course, now what may not be as obvious, and it sort of shows how nice the theory is of complex numbers, is that if I take now the norm of AB, say square, right, what do I get? I get AB, right, and then I get AB conjugate. Right, remember, complex numbers commute, right, so I can change the order as I want, but this is A, B, let me go into another. Right, this is A, then there's okay, let me do all the calculations more carefully. Right, I'm just using commutativity. Right, and because we know it's norm squares, and then the norms, we define it to just be a square root of this, the positive one, then we get that AB is equal to A. So this sort of the norm or the modulus of a complex number is multiplicative, which is not, it's not obvious, right? If you try to think of creating some kind of multiplication of vectors and want it to satisfy this problem, it's not quite obvious how to do this, right? But here we have this very nice thing, and of course, same thing. If beta is not 0, then just by exactly the same type of proof as before, A over beta is just. Right, you just make A over B be a variable and work out the equation. Right, so it's just pure housekeeping again. Right, but now we can try to see, what happens if I take the norm, I mean, it's easier to work with modulo squared, so I'll take the squares always to try to see what's going on. If I take the modulus of the sum, then what do I get? I get A plus B times A bar plus B bar. Right? I get A plus B bar, but I can make the bar go inside the sum. Then what is this? I get A bar, right, plus A B bar plus B A bar, but this is just conjugate of A B bar, right? I mean, there's maybe an awkward way of writing it, but so I have the same thing here. Right? But when I take a number plus a conjugate of the same number, right? I'm taking like alpha plus I beta plus alpha minus I beta, the betas cancel, so I just get 2 times the real part. All right, so this is just 2 times the real part of A beta bar. Right, and so basically that norm, right, this is the norm of A squared. The norm of A squared plus twice the real part. Right, so it's not quite, the norm isn't additive and doesn't work out quite as nicely as the multiplication when we do addition inside the norm. But if you recall in your algebra, this is feeling a lot like some kind of inner product. Right, that's sort of the role that this term is playing, and we'll see that in a second. Okay, so we have a little more housekeeping to do. When you're learning something in math, I guess maybe it's a bit too much to separate them into only two kinds, but there's sort of 2 kinds of statements, right? There's the housekeeping ones, and there's the sort of surprising ones, right? The things that you weren't expecting. And in the beginning, you have to do a lot of housekeeping just to define things, make sure they're definitions that make sense, that satisfy the properties you want, to create some calculus so that you can calculate things later on. But already today, you'll see some surprising things. But for now, it's just sort of housekeeping. We're just making sure that these definitions work out the way we want them, and giving ourselves some statements to use later when I want to show you the actual surprising things. Okay, so we have, of course, lots of interesting inequalities, or useful inequalities, I should say. Maybe they're not particularly interesting at this point. But it's kind of clear that, if I take the real part of a number A, right, again, if you think of A as being alpha plus I beta, of course, the size of the real part will be smaller than the norm, right? Because the norm is the square root of the sum of the squares of alpha and beta, right? I wrote here in terms of the norm square, but of course, the norm is now the square root of alpha squared plus beta squared. So in particular, alpha is always smaller than this, right? And so is minus alpha. And so the real part of a number is always between its modulus and its modulus. Right, it's just saying that an entry in a vector is always smaller or equal than the norm of the vector and bigger or equal than minus the norm of the vector. Same thing for imaginary part. Right? Okay, but in particular, if we now apply it here, we already get something, right? So let's just apply this very simple inequality to this expression up here. So what do we get? Right, we have that this is the norm A squared plus the norm of B squared plus twice the real part of A, B conjugate, right? But because of the inequality, this is smaller or equal than the norm of A again, norm of B again, but now I get to replace this by the norm. Right, the norm of AB bar. But the norm of AB bar, first of all, the norm of A and A bar is the same, right? Because the beta just switched to minus beta, nothing changes. Right, so this is equal to A squared plus B squared plus 2 norm of A times norm of B. Okay, but now you might recognize that this is a familiar square. So in particular, right, we get that the norm of A plus B is smaller or equal than the norm of A plus norm of B. Right, this is nothing else than what we call the triangular inequality. Right, it's just a triangular inequality, right? We're just recovering it from analytic definitions of conjugates and norms and things like this. And of course, you can do this with any number, right? You don't need to do it just with A and B. You can do if I have A, B, C, D, and so on, of course, the norm of the sum is going to be smaller or equal than the sum of the norms, and the proof is exactly the same. Okay, so we're almost getting into the first surprising statement, not quite yet. But so the other inequality that is very, very familiar from the linear algebra is Cauchy-Schwarz. So there'll be, we also have Cauchy-Schwarz here. Right. Cauchy-Schwarz will just tell us it will be the same thing with complex numbers, that if we have a sum of AI BI, right, think like inner product, and this is smaller or equal than AI. Right, times the, oh, I forgot a square. Right, I forgot a few squares. Okay, and of course it's the same thing exactly with when I take right, this is just Cauchy-Schwarz for the complex numbers. Exactly the same. Right, and the proof is exactly the same as proof. I won't prove it all the way, but it's the same as linear algebra. It's the same as linear algebra over the reals. Right, and the proof you just take, you also start it. Right, it's the exact same trick. Right, and the sum, of course, is from I from 1 to n. I won't write everywhere, but for whatever n is. But of course, all of them are with the same sum. Right, so you just write ai minus lambda bi squared. Right, if you have a sum of absolute value squared, so this for sure is bigger or equal than 0, and then you expand this out and pick the right lambda, and you recover Cauchy-Schwarz. Right? Sure, you've seen this in linear algebra, so I'll spare you the details for here because they're exactly the same. Right, so. Okay, and in fact, I mean, the linear algebra works just as well over the complex numbers. I would say even better over the complex numbers because it's much easier to do spectral theory because, right, an eigenvalue for a matrix is the zero of some polynomial, right? Is the solution of some polynomial equation, the characteristic polynomial. And so because equations over the complex numbers all polynomials will have roots, then it actually allows you to do spectral theory of many more matrices that you could do over the reals. Okay, so let's start with, let's get to things that are a little more interesting. There's still a bit of housekeeping, but we're going to get to things that are going to be more surprising. And so one is that, I've done everything sort of analytically, but really, right, it's kind of clear that the complex numbers are related to a two-dimensional real vector space, right, where I just consider the R2 as one axis being the real axis and the other one being the imaginary axis. Right? And in fact, this is a very useful way of thinking about the complex numbers. Right? To think of this as the real axis, and this is the imaginary axis. That is, and then we think of all of this as the complex plane. And it's very useful to think of complex numbers as just a point in this plane, right? And this is a very, very useful picture to draw many, many times. So, right, if I have a complex number A, which is equal to, say, alpha plus beta, right, then I draw it in a place where, right, the real part is alpha, the imaginary part is beta. Right, and of course, here, minus A will be here. A conjugate will simply be a reflection on the real axis. This will be A conjugate equals to alpha minus I beta, right? I just flip the imaginary part. Right? Number 1 will be somewhere here. Number I will be somewhere here. And minus I and minus 1. Right, and of course, to be complete, this is going to be minus A bar. right? I take A bar moves me over here, and then the minus moves me all the way over there. And now it's also a few things become quite clear, right? That if, the length of this line is exactly, right? The length is exactly the modulus of A, right? Because what is the length? Just Pythagoras theorem, right? It's just square root of alpha squared plus beta squared, right? So A bar really measures the length of this line, so that's good, right? It makes it the theory we're building, the norm, the length, or the modulus of the complex numbers are actually their length. If we think of them as vectors in R2. All right, so addition is also very simple to understand, right? If I have, say, another number, say, let me put it in a way that, okay, let me say I have another number b. Maybe let me go somewhere. Okay, I'll try to, let's do it here. Okay, if I have some number b, then a plus b is exactly like addition in is just the same as addition as vectors, right? There's nothing mysterious about addition, right? And subtraction and all this are just the same as operations over R2. Now, what's not obvious in this picture is what does multiplication look like, right? I guess and this is where things start to get interesting, right? Can we visualize? Okay, so I have two numbers I can think of them as vectors in R2. How can I visualize their product? And now it's not completely obvious, right? Because the product is a weird operation, right? It wasn't completely clear what it means in particular, right? If I have, let's write it down, right? If I have alpha equals, A equals alpha plus I beta, I say B equals X plus I Y, right? What was AB? AB is alpha times X, right? Then these terms also become real, minus beta Y plus Y, and then I get the product of alpha Y plus beta X. Okay, now think about what this would look like in the picture. It's not clear. I'd say this is one of the first things that's not just housekeeping. It's really not clear what the answer is going to be. Take 10 seconds to just think about this. If I have a number A and B, and I want you to draw the number A times B, it's not obvious. I mean, you can, of course, work out these things and see where it goes, but it's not clear at all, I would say, from just looking at it. Okay, so I'd say this is, the first non-housekeeping thing that we're going to do today. There is, however, something we already know about it, right? We know what its length is going to be. Right, because we know that the modulus of the product is the product of the modulus. So we know that it's going to have the length be the product of the lengths of A and B. Okay, so I have, let me make some bigger axes. I have a number A. Right, and my goal is how to visualize A times B. Okay, and let's say we have some other number b. Okay, so I want to take their product, and the question is, how can I visualize this operation? So what do we know about it? Right, what we know about it is that the product, the absolute value of this number is equal to the absolute value, or the modulus, of the product. So we know that in terms of their length, there's something, we can understand it. This is, maybe visualize, I'm not sure is the right word, but we can at least understand what's going on. Right? In particular, it's not sort of scale invariant, right? If I want to draw this picture, it depends where I put the 1. Right? But it's suggesting already that we should try to think we should think of a number in terms of its norm and something else. Right? Because the operation is very predictable on the norm, it's suggesting that we should think of a number as the norm and something else that decides that can tell me what the number is. Right? This is exactly what polar coordinates do. Right? So polar coordinates are exactly a way of representing numbers in a way that you get, the size is one of the things you learn about the number, the length, and you learn also the angle. Right? And so let's say, maybe let me erase b so that it's not, so I have a bit more room. Okay, and let's say I have an angle 5. Okay. Let's go. Okay, so now I can represent the number a by the angle and the length. Let me call it r, right, in the normal language of polar coordinates. Right, so I can now write a as r times cosine of the angle plus sine of distance. Right, and this now is completely well defined. Right, and of course, r is just the absolute value of a, then modulus of a, and phi, I'm going to call, it's the angle of a. In complex analysis, we call this the argument. Right? Of course, it's not, it's only defined, from 0, say, to 360 degrees or 2 pi. Right? If I add 360, it's exactly the same, and if I add 2 pi, it's exactly the same. That's fine. Okay, so now, let's say that we have another number, right? So let's say that we have two numbers, right? A1 equals, so R1 times cosine phi 1 plus pi sine plus phi 2. And 2 cosine of phi 2. No, phi 1, sorry. Okay, so now what we know is when we take the product. Okay, let's take the product to see what happens. Okay, so let's take the product of these things. So we get R1 times R2 times some nasty expression, right? Let's write it. Now the hope is that somehow this simplifies. Right? But if you think about it now, it's not, because we do know that the modulus of A1, A2 is the modulus of A1 times the modulus of A2. So this is the right representation in polar coordinates. This is really the new R. Right? It could have been that when we do something like this, the term here is not like something of norm 1, right? It could have been that it's not cosine of something plus I sine of something else. Right? A priori, there would be no reason for that to happen. But you know, if we take the product of these numbers, this really is the new R, right? Because we know that the modulo, the norm of A1 times A2 is the norm of A1 times the norm of A2. So we know that this has to be, right? This has to be the cosine of something plus I sine of the same thing. We just don't quite know exactly what it is yet, but we know that it must be of that type. Okay, but now let's work a little harder. Okay, so what do we get? So real part first. We get cosine by 1, cosine by 2. Then the other part, the other contribution to the real part comes from the cancellation, the I squared equals minus 1. We get a minus, sine of phi 1, sine phi 2, plus, now we get the imaginary terms, right? Cosine phi 1, sine phi 2, sine phi 1, cosine phi 2. Okay, so. Okay, now go back to your formulas in trigonometry, and you might remember that this is just a formula for the cosine of the sum. And this is the formula for the sine of the sum. So you get a very, very unique formula for the product, right? That gives it an interpretation or a way to visualize. Is that A1, A2 is equal to R1, R2 times cosine of angles plus I sine of the sum of angles. Right? So the modulus of A1, A2 is equal, as we knew already, A2, but also the argument of the product is equal to the sum of the arguments. And this, I would say, is not just housekeeping, right? It's a priori not obvious at all. Right, and so in particular, if I have a number A, let's say that they are in the, let's say that this is the numbers of modulus 1, right? And I have another number, say B, with some angle theta, then when I take the product, because I drew the picture so that they have norm 1, so that nothing happens to the modulus, A times B will just be the sum of the two angles. Right? And so we have a nice way of visualizing products. Right? What they do is they multiply the norms and they add the angles. Okay, so this I think is one of the first, not simply housekeeping things. Okay, and of course, you immediately get a bunch of things from here that I'll do in the last 2 or 3 minutes, and then we'll take a break. And then if you want to see some of this in more detail, just go on the book. This is, I think, at the very end of maybe chapter 1. I'm even using the same notation, I think, so it should be very easy to go and see it there. Right, so this is one of the most interesting things. The argument of the product is just the sum of the arguments. Okay, of course, one needs to be careful. The number 0 doesn't have an argument, right? It's not well defined. The number 0 is norm 0. It doesn't make sense to talk about its angle. So right, we have to be careful when we talk about 0 in this sense. But also, it's not hard to show that if I take the argument of the quotient, that this is just right, that this is just the difference of the argument, right? You can just take one as a variable and work it out. It's also not so hard to see that, because some of these angles are the same. Right here, because they're all norm 1, it's even easier to see. But even when they're not norm 1, you can see that a bunch of these angles are the same. And because the modulos are multiplicative, the way that the triangles grow is also very predictable. So you can work out that there's lots and lots of similar triangles when you write the triangles between, say, 0, 1, and A, and things like A, B, and 0. You see that a lot of these triangles are similar in the sense of Euclidean geometry. And you can work out a lot of interesting geometric properties that way, which I won't do here for now at least, but you can see them on the book. Okay. And you just see if I want to say anything else before. No. I would like, it's important to say that, right, all of this happens modulo 2 pi. Right, or modulo 360 if you like working with degrees. Right? Clearly, all of this is defined. The angle is defined modulo 2 pi. So when you take, operations with angles, you have to do always modulo 2 pi. Okay, so we'll take a break now, and we'll be back. Back in 15 minutes.